Hello and welcome to Nerdy Nisa. Today we're going to be going through spontaneous and non-spontaneous redox reactions. Firstly, let's just understand what we mean by spontaneous and non-spontaneous. Spontaneous reactions are reactions that happen pretty much instantly. They don't really need startup energy because they're just so willing and so excited to partake in the reaction that you don't really need anything to get them started. And non-spontaneous reactions are ones that are pretty apprehensive of each other. They don't really want to react, so they're not really keen on it. They're going to need somebody to push them together, some sort of startup energy, in order to get that reaction rolling. Now, to understand spontaneous and non-spontaneous reactions, we're going to need to understand the standard table of electrode potentials. Now, this table is brought to you by the IEB. Credits to them because it's a really lovely table to look at. Now, let's understand how the table works. As you go up, we have an increasing strength in the reducing agent, and as you go down, we have an increasing strength in the oxidizing agent. What does that mean? It means that as I go up and up and up the table, I have my substances attracting their electrons less. They don't really attract them that strongly as we go further up the table. Why is that the case? Well, to be a good reducing agent, you need to be something that helps other substances reduce, which means you need to be a really good provider of electrons so that they can gain those electrons. That means you have to really not care about those electrons. You don't want them for yourself, so you're pretty fine to give them up to others. So if you look at something like lithium, it does not care about its electrons that much. It's very happy to give them away and help other substances reduce. So as you go up, the pull to electrons becomes weaker. Now, the inverse is true as going down. As you go down, these substances are pulling their electrons so much stronger because to be a good oxidizing agent, you need to yank electrons out and off of other substances. So something like fluorine is really good at oxidizing other substances because it just takes their electrons, right? It just yanks them because it's super greedy and it wants it for itself. So that's essentially how it works. Going up, you have weaker pulls to electrons, and going down, you have stronger pulls to electrons. Understanding what goes up and down, let's understand what goes left and right. So if I go right across my table, I have a reduction reaction because I have some sort of substance that then gains an electron to then become a new substance. So if I look at something like this, I have magnesium ions, which gain two electrons to then become a magnesium atom, part of magnesium metal. So that's a reduction reaction. Now if I go the other way across my table, this would be an oxidation reaction. That's because I start with some sort of substance, and then that substance loses an electron to then become some sort of ion. So if I look at platinum over here starts nicely as a metal, but then it loses its electrons and it becomes platinum ions, right? Platinum 2 plus. So that's essentially how you read it right and left. Now that we have a basic understanding of that, let's understand how spontaneous and non-spontaneous reactions work. For a spontaneous reaction to happen, you're going to need a very strong reducing agent paired with a very strong oxidizing agent. That's the basic premise as to how that works. Now, if I want to actually determine whether something's spontaneous or non-spontaneous, I generally can do this in one of three ways. We're going to go through all three today. The ways I like to see it is firstly, is the substance happy with where it has been placed? The second thing is let's look a bit more scientific and look at the type of agent it is and the strength of that agent that it generally has. And then the last thing we're going to look at is essentially the gradient of the line you can draw between them. Now, some of these aren't that scientific, like whether the substance is happy, but I think it's very helpful to help you remember it. And the main bottom line that we need to remember for all of this is that it's always relative. Now, that's something you're going to understand as I explain the rest of this. So let's just firstly start with the happy thing. To understand whether substances are going to be happy, we need to know what they like. Now, going down the table, because we know there's an increasing strength of oxidizing agents, we know there's an increased likelihood that you just want to be reduced. You want to undergo reduction. right? Because if you're a strong oxidizing agent, that means you want to yank electrons, you want to undergo reduction. And if we go up the table, you're somebody that really wants to undergo oxidation because you're a really good reducing agent, which essentially means that you really don't want your electrons, you're happy to give them away, so you prefer to lose electrons and undergo oxidation. So let's then take a random example. Let's say that I have something like copper ions and I have zinc metal over there. Let's see if that's a spontaneous reaction. Let's look at them each individually. Let's see if they're happy. Copper over here is the lower of the two. That's what we mean by it has to be relative. So out of the two, this one's lower on the table. So we're going to look at the downward arrow. So going down, it prefers reduction, right? So out of zinc and copper, copper prefers reduction more. Is copper being reduced here? Yes, because the half reaction you have, it has copper ions plus 2 electrons gives you copper metal. So yippee, copper is so happy because it's being reduced and it prefers reduction. So copper over here is a very happy chappy. Then if we look over here at zinc, because it's the higher one up, we're going to look at the upward arrow. This upward arrow shows us that zinc prefers oxidation, and in the half reaction we see here, zinc undergoes oxidation. Zinc loses 2 electrons. So zinc is also happy. It likes oxidation and it's experiencing oxidation, so a very happy chappy indeed. So I know it's definitely going to be spontaneous by that measure. But let's also look at the scientific way. Let's look at the type of agent it is, and this is how you're going to be answering questions within your papers, right? So the type of agent it is. Copper, as you can see, is further down on the table. That means it has a strong sense of being an oxidizing agent. It is really good at taking up electrons. So relative to zinc, it's the stronger oxidizing agent. And in this half reaction, copper is taking up electrons. So it is fulfilling its role of being a strong oxidizing agent. And over here, zinc is relatively a stronger reducing agent, and here it's fulfilling its reducing agent role by taking its electrons out of itself and giving it to others. So here we have a strong reducing agent. So there we have it, guys. Based on the type of agent it is, it's also spontaneous. And the last way that we can measure this is by looking at the gradient. The gradient between these two is increasing. So because it is an increasing gradient, I then definitely know that this is some sort of spontaneous reaction. Now let's invert this reaction because the inverse is going to show us something slightly different. Let's say that I've got zinc ions and I've got copper metal instead. Now, let's evaluate each one individually. Firstly, are they happy? Well, here we have my zinc ions. Now, because zinc is further up on the table than copper is, it's going to want to have oxidation happen to it. And in the reaction, it doesn't have that. In the reaction, zinc is supposed to gain electrons to become zinc metal. These zinc ions are meant to gain electrons and become reduced. So it's really unhappy because it's meant to undergo reduction, but it just wants oxidation relatively. And then if you look at copper, copper is further down than zinc, so we're going to look at reduction. So copper really wants to undergo reduction. But in the half reaction, copper metal is supposed to lose electrons and become copper ions. So it's also really sad because it's supposed to undergo oxidation, but all it really wants to do is be reduced. So it does not pass the happiness test. Then if we look at it as a type of agent, if you look at zinc, zinc relative to copper is a stronger reducing agent. So it's supposed to take up a lot of electrons. It's supposed to give up a lot of electrons because it's a reducing agent. But as you can see, zinc is taking up electrons, so it's not very good at its job. It's not going to be strong at that. And over here, copper is further down the table, so it's a strong oxidizing agent. But as you can see, copper is supposed to give up electrons, and it's not really good at that because being an oxidizing agent means you attract electrons strongly. So it is not strong as the type of agent. We've got a weak agent on this side, and we've got a weak agent on this side. Up here, we have a weak oxidizing agent, and over here we have a weak reducing agent. So it's not looking too good. And then in terms of gradient, if we are to draw our gradient between these two, it goes down. It's a negative, wait, let me put that in red. It is a negative gradient. So that is definitely not good, and it shows us that once again it is a non-spontaneous reaction. I hope that this video helped young scientists. If not, and you have any questions, please leave them in the comment section down below.